Good morning. This is the Modern Physics class, Physics 308, and today is Friday, April the 3rd. I wanted to pick up where we left off last time and take a look at this diagram with the decay of copper-64. Not shown is the horizontal axis, which is the atomic number of the elements involved. Nickel here is 28, copper is 29, zinc is 30. And also the vertical axis, which is not shown, which is the mass energy. So you can see from this diagram that copper has the largest mass, but these are all atomic mass number 64 elements. And it shows here the decay of copper, which is unstable because it's not the lowest mass of the atomic mass number 64 elements. Then copper here has two possible ways of decaying. And so I want to look at all the nomenclature that's here and help all of us get a little more familiar with the information. Of course, you can see the atomic number 64, the atomic mass number 64, the atomic number 28, 29, and 30 is not shown. Also, the lines in bold that are horizontal represent the value of the mass energy for the particular element that is labeled underneath them. If I look at copper, there's a 1+ there, and that refers to the ground state of copper. And the other two bold lines for nickel and zinc show 0+ for their ground states. Nickel also has a 2+ excited state shown. So let's figure out a few things and get going. First of all, how many neutrons does copper have? And I'm going to stop and let you take a look. Or if you'll stop your video and take a look. This is what you should have calculated, that there are 35 neutrons in copper. Simple calculation. Sometimes it's easy to forget what you're doing here. Let's look at the energy levels that were indicated, the 1+ and the 0+ and the 2+, and the 1- I should say, and see if we can't understand a little bit about the shell structure. So in order to do this, we need to go to our shell structure diagram, which will pop up in just a moment. And we need to calculate for each energy state how many possible protons can exist at that energy state. For example, a 4d7 halves has an angular momentum quantum number of 7 halves, and that means its Z component has 8 possible states, all listed right here. And from this, we can also know that the D state is an orbital angular momentum state with a quantum number 3. Remember, S is 0, P is 1, D is 3, D is 2. F is 3, G is 4, and so on. Need to correct that. All right, so I'd like you to take about 10 minutes, 5 minutes, and for states all the way up to 5g9 halves, I'd like you to calculate how many protons can be in each state. So let's pause here while you do that calculation. That is, you pause your video. Now we're back, and here are the answers that you should have gotten. If you didn't, you might talk to some other people in class or send me an email about this or the follow-up in a few minutes with class. One thing to notice is that there was a small energy gap, bigger than the other energy gaps. And those gaps act kind of like the breaks in the binding energy in the atomic electrons in the periodic table. And that when this particular state, for instance, is full with 2 protons, the next proton that's added it takes a lot of energy to get it there. So this is a stable configuration. And that's what we find that nature has done for us also, that elements with 2 protons are more stable than elements with 3, meaning that their binding energies on the average are greater. Same thing with the next break that tells us 8 is another what we call magic number, and then 20 and 28 and 50. And if you kept going, because you do have the whole table, you can figure out that the next one is 82, and the next one after that is 126. And the one after that, 184. I'm not sure the table I gave you goes up high enough for that. All right, we're going to use this information to look at nuclear structure. So we're going to be doing some angular momentum addition, which we've done before and which you had a handout on and you did some work. It's a little bit different with the nuclear physics, though, because we've got 2 sets of particles that are filling the same energy states, but following the rules only for themselves. So there's rules only for the protons and rules only for the neutrons. So when we do this, if we end up with an even number of protons, the protons will pair up and cancel their angular momentum. The same thing happens with even numbers of neutrons. They pair up to give 0 angular momentum for the neutrons. And so if we've got a nucleus with an even number of protons and an even number of neutrons, our so-called even nucleus, then the ground state, which is what we're talking about here, has no angular momentum and will have 0 for the angular momentum state. The parity is another issue that has to do with the symmetry of the wave function. So if I take the position of all the nuclei at any one point, take all the protons wherever they are in space, move them through the origin to the opposite 3-dimensional point in space. That's called, that reflection is what determines the parity. So if the wave function, when I take all those particles and reflect them to their opposite position, if the sign of the wave function changes sign, it's called an odd parity. And we use the symbol minus for that. If when we reflect all the particles through the origin to their opposite position, and the wave function doesn't change its sign, then it's called an even parity, and we use a plus for that. So for a ground state with an even number of protons and neutrons, because of the evenness of all of that, we'll have a 0 plus state. Well, if we've got a nucleus with an even number of protons and an odd number of neutrons, for instance, A equals to 41, well, the protons all cancel out and give no contribution to the total angular momentum. But with the neutrons in the ground state, 20 of them are paired up, and we've got one odd neutron left, and its angular momentum is going to be the angular momentum of the ground state of the nucleus. So if you look back at the previous slide with 21, if we go here, 20 neutrons fills up the 2s1/2 state. The next neutron will be a 4f7/2. And while we're here, let me mention, this is a somewhat non-standard nomenclature for the what we would call the N number for electrons. Most people will use, for the first P's, will use 1p for both of these. And for the first D's, they'll use 1. The table that I got this from used the atomic number designation, which most people do not use. All right, so if we go back to our neutron, then since the unpaired neutron is a 4f7/2, or normal nomenclature is a 1f7/2, the ground state is a 7/2, and if we go back SPDF, F is a quantum number 3. That's an odd number, and so -1 to the sum of all the orbital angular momentum quantum numbers of all the particles involved. Well, if you've got 2 of them, it's always even. So it's only the leftover ones. That will be 1, or it'll be 3 for our F state, and -1 to the 3 powers is negative. So we have a 7/2 negative state where the quantum number is 3 for the F. So let's take a moment. I'd like you to work the problems for these isotopes and a couple that are rule breakers. So we'll take a couple of minutes here to have you pause your video and work these out. Then we can look at the answers. So here's what you should have gotten. It's pretty boring stuff. I selected things that were all clustered around the extra particle being in the 4f7/2 state, except for the 39. And the 39 there was one missing, and that can be a challenge. So we'll get back to that a little bit later. Then the rule breakers here, potassium 39, calcium 39 are 3/2 plus. Can you tell me what particle got promoted? And while we're at it, let's throw in one that's not up here around mass number 40. Let's jump to oxygen 17 and see what you get. I'm going to have you pause here while you do that work. All right, now that you're back, I'm going to leave it there. I'd like you to mull that over and not just give you an immediate answer. During our discussions in class, we'll look at those answers. So here is the energy level diagram for mass 130. I gave you a spreadsheet for the Weizsäcker equation, and I've updated that. If at noon today, if you'll take a look at it, I'll have a graph of all of these calculated, and you can compare that graph with this data. So the point here is that there's quite a bit going on in these decay processes, that there are many different types of excited states, and those excited states are not easily understood from the shell model. For instance, calcium-41, its one neutron is in the 4f7 half state. Thinking back to atomic electrons, we would think the first excited state then would be the neutron being promoted to the next energy state. And if you look at the next energy state, it would be a 2p3 halves state, which would be a 3 halves minus, p is a 1, a 3 halves minus state, promoted up from the 7 halves minus ground state. And it is. Whoa, well, what was I saying? This doesn't work. But if we go to calcium-43, the same thing should happen, but no. The first excited state is a 5 halves minus state. Every now and then it works. And that's a very fun thing to find. Most of the time it doesn't. And when you get to the second excited state, it almost never works. So the shell model does a good job for most ground states in predicting the magic numbers, but not much success can be had for excited states. That's because the spin-orbit coupling in the nucleus is 20 times bigger than it was for the electrons, where it was just a small change. And so when you excite the atoms, atomics, the nuclear states, this spin-orbit coupling that we can calculate in our static model doesn't take into account all the changes that take place in the nuclear frothing of protons and neutrons, giving us a very dynamic change to the spin-orbit coupling. Let's just look at uranium-238 as an example. When we look at this, it doesn't fit energy gaps at all that we might expect for the shell model. As a matter of fact, these energy states here are best described by the rotational energy. That is, that the nucleus can be thought of in these excited states as rotating faster and faster. And so for the 0 plus, 2 plus, 4 plus, 6 plus, 8 plus, 10 plus, 12 plus states, all of those fit very nicely into the energy L times L plus 1 h bar squared over I for a rotational quantum state. So unlike the electrons in an atom, where we have one good theory that can, with a lot of work in some cases, predict the energy states, with the nuclear models, we have more than one model, and they apply better in some states than others because the total calculation here is incredibly difficult. So let's go back to the beginning and let's figure out some of the last things that have to be explained here. A couple things I noticed disappeared from my graph here. One is that this decay from the 1 plus state down has an electron capture component to it that's about 3 times more probable than the beta plus decay. And the decay from the 1 plus to the 2 plus state only happens 0.54% of all times when copper decays. So these percentages here are referring to the parent, which is also some nomenclature we need to discuss. We have the parent, which is the isotope at the beginning of all the decays, and the daughter, or in this case, daughters, which are the byproduct of the decay. And should the daughters also be radioactive and decay, you have granddaughters and great-granddaughters and so on. The decay mechanism is indicated here, beta plus. We're throwing a positive charge out of the nucleus, and it makes our copper lower its atomic number for its daughter. Whereas when we throw a negative charge, which comes out as an electron, but it's not an atomic electron, it's coming from the nucleus. This electron leaves behind an extra positive charge, and the daughter increases its atomic number. Sometimes, instead of beta plus decay, an atomic electron is actually consumed with a proton in the nucleus to create a neutron. And the effect is the same. We've reduced the atomic number by 1, and it looks like it could have been a beta plus, but in fact, we never see a beta plus coming out. All we see is an X-ray for the when the electrons fill the vacancy by the electron consumed by the nucleus. So that's called electron capture when that happens. And it competes with the beta plus for the decay probabilities. So I want to look at a little bit about predicting the energies of the beta particles and the electron capture effect. So beta decay, beta minus decay, is where a neutron decays to a proton, an electron, which is called a beta particle, and an anti-neutrino here, which I couldn't get the anti sign to work. So the neutrino has a very small mass, and when we look at mass energy considerations, we just ignore it. Of course, the beta has a very small mass compared to the proton, but not small enough to be ignored. So if I use mass energy conservation and I include in here something called the Q, I'm going to say the mass energy of the neutron is going to equal to the mass energies of the protons, the beta, and the neutrino, plus the sum of all the kinetic energies, and that's the Q. Now, this is a relativistically correct way to describe what's happening here, since the total energy of a particle is the kinetic energy plus the mass. It's just that the kinetic energy here is not 1/2 mv squared. It's a relativistic kinetic energy. All right, so here's the Q, and this is the Q up here. There's a slight recoil when the proton and when the neutron decays to the proton and the beta in order to conserve momentum. But for it goes in the ratio of the masses of the two particles. So the proton has a kinetic energy that's the ratio of the beta particle to the proton particle masses. And that's like 1/2000. So we get less than 1/100% of the energy going to the proton. So we're going to ignore that here. And I find that the Q then will just be the difference in the parent mass and the daughter mass and the particle that was ejected mass. But something interesting happens here. The neutron and the proton masses, well, the neutron mass is a table mass as the proton mass is, but the proton mass plus an electron mass is the mass of the hydrogen atom. So we find it's much more convenient with our tables to think of the Q as the mass of the parent, in this case the neutron, minus the mass of the daughter, in this case the hydrogen. And that's how we're going to think about it, and that's how we're going to calculate things. So here's the generalization. The Q for beta minus decay is the parent mass energy minus the daughter mass energy, where the daughter has an atomic number that's 1 bigger than the parent and a neutron number 1 less than the parent, but the same mass number. And Q will be considered in our thinking as the maximum kinetic energy of the particle. But because there are 3 particles emitted, the neutrino, the beta, and the proton, in this case, or the nucleus of the daughter, the energy can be shared in every possible way between all these particles. So we can have a beta particle that has almost no kinetic energy, and a neutrino that has almost all of the energy, but it just never has any mass to speak of. So we like to think of Q as the maximum energy of the beta particle because that's something that we can measure. So let's take a look here and take our copper 64, if you would, calculate the Q, and you can convert from AMU to MeV with this simple rule. So we'll pause here while you do that calculation. And we will pick up with this later on. Thank you.